All right, let's see if we can finish up Chapter 5, Part 2. So we have a little bit of a reminder about what the inverse of a function is. So we have to go back to composition of functions. So we're going to start out with a function going from x to y. Recall that we say that a function is bijective if it's both one-to-one and onto, namely we have a one-to-one correspondence. One-to-one and onto is just the same as both injective and surjective. So if you recall, if we're both injective and surjective, then what we have is for every element of the codomain, we have exactly one element in the pre-image. And if you think about that, what that means is we can define a map going backwards. So what's that map going backwards going to be? It's going to be going from y to x. And we're going to be composing those functions. So just as a reminder, if I have any situation in which I have a map from going from x to y, I can compose it with another function that starts at y and goes anywhere else, which is called the following function, the composition of g and f. And what that map does is it starts with x. It first applies f to x to land in where? In y. And then it applies g to the outcome to go from y to z. So this will give me something inside of z. Now in the case that we're looking at the inverse of a function, so if we're looking over here at the inverse of a function, then we're not just looking at any old map going from y to somewhere. We want to go from y back to x. We started with a function that went from x to y. Now we want to go backwards from y to x in such a way that if we look at it, we're going from x to y and then back to x. We want to start with a little value of x. It goes to f of x, and then it goes back to x, which means what we have in the composition is the identity on x. But equally, if we had started from y and gone to capital X and then gone back to y, this is my h and this is my f. Up here, this was my f and this is my h. Notice that this is still an identity function. I take y to some little x. This is h of y, which is some x. Then my f should take me back to x. And so now I get the identity not on x, but I get the identity on y. So when we want to show that a function has an inverse, we have to show two things. One is that the composition first doing h, then doing f is the identity on y, and the other composition, h following f, is the identity on x. And so the first thing we need to do is we need to justify the idea of the inverse. So we call a function that has an inverse invertible. So the statement is if f maps x to y is invertible, then its inverse is unique. So the inverse is a justifiable statement. So what do? We do as ever, we suppose we have two of them. So suppose we have h going from y to x, let's call it h1, and we have h2 going from y to x, and they're both inverses, such that, so what does it mean that they're both inverses? It says that f following h1 is the identity on y, and h1 following f is the identity on x, and f following h2 is the identity on y, and h2 following f is the identity on x. Okay, so we have got a lot of stuff going on. So let's suppose we have a little y contained in capital Y, and we want to show that h1 of y is equal to h2 of y. Right? That would show that h1 equals h2. That's what it means for two functions to be the same. We have to show that they're equal on all elements of the domain. Well, what do we know? We know that we could take little x1 to be h1 of y, and we could take little x2 to be h2 of y, and what we want to show is that x1 equals x2. Well, for lack of a better idea, we now have something, so we have a little x1. Where does this x1, what does h do, right? So h1 takes my little y, and it maps to x1, and it takes my little y, and it maps to x2 under h2. So what I could do is use my f to go backwards. So consider f of x1 and f of x2. Okay, so what are those? Well, that's f following h1 of y, and it's f following h2 of y, right? But what do I know that f following h1 is? F following h1 from back here, maybe I'll highlight it because that's always fun. So let's highlight it in yellow. F following h1 is the identity, so that's equal to the identity on y of y. And this similarly, f following h2 is the identity on y also. So this is also the identity on y of y. And so that's equal to y, and that's equal to y. So thus, f of x1 equals y equals f of x2. And now what do we know? We know that our function is invertible. F is invertible. So let's see if we can get something out of that x1 and x2. So now we know, we can't really say, oh, it's 1 to 1 and on to. We haven't shown that yet. But what we can show is now we've got f of x1 is equal to f of x2. What we can do is now we can apply either h1 or h2. It doesn't matter which one. So we look at h1 following f of x1. That should be equal to h1 following f of x2. Right? I'm just applying h to both sides of this expression. So of course they're still going to be equal. But then remember h1, see, h1 following f is the identity on x. So that tells me that this is the identity on x applied to x1, and this is the identity on x applied to x2. And so we get x1 is equal to x2, which was what we wanted to show. We wanted to show that over here, we wanted to show that h1 is equal to h2. We started with two supposedly different or putatively different inverses. We wanted to show they were the same. The way we want to show that they're the same was by showing that they act the same on the domain. And so we named x1 and x2 the image of any particular element, any arbitrary element in the domain, and what we've shown is that they're equal. So what that tells me is that h1 equals h2 as desired. So the inverse is indeed unique. So if we look back to the functions above, you might want to pause the video and just go back and check which ones of these functions that we looked at a while ago were injective, surjective, and bijective. And so if we look at them all, you should be able to convince yourself that, let's see, the sign is neither injective nor surjective, so it doesn't have an inverse. This guy here, tells me that 1 and 0 map to the same place, so it's not injective and bijective. This one, number 3. Number 3 is a bijection, and indeed we have an inverse function. H equals to f inverse would be h of x equals the cube root of x. Oops. Then you should look through the other ones and decide whether they're injective and surjective, and we can discuss that in class tomorrow on Monday. So it's only number 3. Finally, I want to prove one of these. I think you have other ones on your homework, so maybe I'll prove number 3. So these are sort of cleanup lemmas. If you have a function going from x to y and another function going from y to z, if you know one of them is injective, do you know the composition is injective? Those kinds of statements. So remember, we're going from x by f to y and by g to z. So what we're proving in 3 is we're assume g following f, which goes from x to z, is injective, and we want to show f is injective. Well, how do we do an injectivity proof? Suppose that f of x1 equals f of x2, and then we just remember we want to show that x1 equals x2. That's what our goal is. Okay, well, if f of x1 equals f of x2, so we've got x1 here and x2 here, and suppose they both map to y, then what could I do? Well, I could use that I know the composition is injective. So what if I take g of f of x1? That should still be equal to g of f of x2. So this is g following f of x1, g following f of x2, and then since g following f is injective, we have x1 equals x2 as desired. So maybe you can give some of the other ones a shot, or we can do them in class tomorrow. See you then. Bye.